Welcome back, everyone, to the second talk of the day. Today we will hear from Jim Wright from University of Edinburgh, who will speak to us on exponential sums and oscillatory integrals, a unified approach.
Okay, well, I hope everyone can hear me. So thank you for the invitation. It's a pleasure for me to talk in this seminar series. So I would like to talk about some joint work with Jean-Marie Dallara. So we have an argument. It's a rather simple elementary argument, but it seems to be powerful enough to give effective bounds for oscillatory integrals in some generality. So we will be able to treat oscillatory integrals with respect to any polynomial phase, and moreover, we'll be able to treat these oscillatory integrals over any locally compact topological field. So let K be a locally compact topological field. So I will always assume that the topology is non-trivial. So from the additive structure of the field, we have a locally compact abelian group, and therefore we have Haar measure, a translation invariant measure, which is unique up to a positive constant. Right, so we have a measure so we can define integrals, but in order to define an oscillatory integral, I need additive characters. And in this generality, it turns out that the additive character group of these fields is in fact isomorphic to itself. So once I've identified one non-principal additive character, which I'll denote by E, all the other characters come from the field elements themselves. I take a field element Y, that gives me a character by mapping X to E evaluated at Y times X. So we see it really doesn't matter which additive character I choose to define my oscillatory integrals. Passing from one character to another character is just a simple scaling, and we'll be able to track the effects of that scaling on our bounds. Right, so we have a measure, we have a character. Now the most important ingredient is the phase function. And here we'll consider a general polynomial phase of n variables with coefficients in the field K. So let me call such a polynomial F, and I can think of F as a mapping from Kn into K. Kn is just the n-dimensional vector space over K, consisting of n tuples of the field elements. And therefore, I can evaluate my polynomial F on my additive character E and integrate over this vector space Kn. So I'm integrating with respect to Haar measure on this vector space, which is just the n-fold product of Haar measure coming from the base field K. And I will insert a cutoff function psi so that the integration, in fact, is just happening over some compact subregion of this vector space. In fact, in this generality, all of these fields have a natural smooth structure. So I can, in fact, take psi to be a smooth, compactly supported function. And so we arrive at our object of interest for this talk, these oscillatory integrals in this generality, and we want to prove bounds for them. And before I write down our first theorem, our first bound for these oscillatory integrals, let's look at some examples. Let's see what these oscillatory integrals look like. How do they manifest themselves for particular choices of the field K? So I'm going to start with the case of the real field. In that case, everything is quite transparent. What's happening? We're just integrating over Euclidean space Rn. Haar measure is Lebesgue measure, and I'm just integrating e to the 2 pi I of a real polynomial of n variables. And of course, these objects arise from many problems throughout an analysis, and there is a well-developed theory for these real oscillatory integrals. In fact, there was a very interesting bound given by Zhang earlier in this seminar series. And I'll come back to that bound. He gave a general bound for these real oscillatory integrals. But for the moment, let's move on. Let's change the field from the real field to the complex field now. And here we're now integrating over complex space, n-dimensional complex space. Haar measure is still Lebesgue measure, but now our phase function is a complex polynomial of n variables. and we will evaluate that on some additive character of the complex field. Now, if we unpack this just a little bit further, we will see that these complex oscillatory integrals are, in fact, they can be realized as real oscillatory integrals. And that's because the complex field is related to the real field. It is a field extension of the real field of degree 2. And therefore, integrating over Cn is the same thing as integrating over R2n. And if we look at the additive structure of the complex field, that's just 2 copies of the real field, we see that additive characters on the complex plane are just products of characters from the real line. And therefore, we're just integrating over R2n, we're integrating a real e to the 2 pi I of a real linear combination of the real and imaginary parts of my complex polynomial phase. So indeed, we see that these complex oscillatory integrals form a subclass of real oscillatory integrals. And this is a general phenomenon. Whenever we have 2 fields that are related to each other, one is a finite field extension of the other, then these oscillatory integrals defined over the extended field can be realized in exactly the same way as we've been doing here as an oscillatory integral over the base field. And so we have 2 perspectives on the same object. We can view it on the one hand as an oscillatory integral over the extended field, and we can view it on the other hand as an oscillatory integral over the base field. And we can take advantage of these 2 perspectives. We can play them off each other. And that's because our bounds are going to be bounds which hold true over any locally compact topological field. And therefore, our theorems are going to give us 2 bounds for the same object. So going back to these complex oscillatory integrals, we will have 2 bounds for these guys. 1 bound when we view it as an oscillatory integral over the complex field, and 1 bound when we view it as an oscillatory integral over the real field. And so it's natural to compare the 2 bounds. And we will see, this will just be a simple exercise using the Cauchy-Riemann equations, that one of the bounds, we will be able to compare the bounds, and one of the bounds will be better. In fact, significantly better. We'll get a power gain in the bound. And this, so we arrive at an interesting self-improving aspect to these bounds. And this is a general, this will hold true in general. This self-improving game actually plays out in a rather limited way in this Euclidean setting because the real field does not have too many finite field extensions, just has 1. But when we move away and we consider non-Euclidean fields, all of these fields will have field extensions of any degree. And moreover, you fix the degree, there'll be many field extensions of that degree. And so this game, this self-improving game, will play out in a much richer way for these non-Euclidean fields. So we'll come back to this. I want to give you some details of this a little bit later in the talk. But let's keep moving on. Let's change the field once again. Let's move now from the complex field to the p-adic field. So this is a field defined with respect to every prime p. Now I'm looking at an oscillatory integral defined with respect to polynomials of n variables, but now the coefficients lie in the p-adic field. So in this case, it turns out that characteristic functions, indicator functions of balls are actually smooth functions in the p-adic field. And therefore integrating over a ball, restricting my integration to a ball of radius r is a smooth cutoff function. Now let's try to unpack what do these p-adic oscillatory integrals look like. And whenever you want to unpack it, you have to do 2 things. You have to, first of all, understand what Haar measure looks like. And on the other hand, you have to understand what are the additive characters, what do they look like. And in the case of the p-adic field, this is not terribly difficult to do once you know the definition of a p-adic number. And one sees, and this is very straightforward, that these p-adic oscillatory integrals manifest themselves. In fact, they are equal to an exponential sum, a complete exponential sum defined with respect to a polynomial with integer coefficients. Some polynomial of n variables, but now with integer coefficients. And the sum is taking place over all n tuples of integers modulo a particular power of our prime p. And of course, these exponential sums, complete exponential sums are a basic object in number theory. And so we see there is some advantage from taking this sort of general perspective to proving bounds in this generality, because if you can prove such a bound, which is valid over any locally compact topological field, then just applying the bound in the case of the real field, you're getting bounds for real oscillatory integrals, and that potentially has applications in problems in Euclidean harmonic analysis, which of course is one of the topics in this trimester program here at Bonn. But if you apply the same bound, but in the p-adic field, you're getting bounds for exponential sums, and potentially that gives you applications for problems in analytic number theory, which of course is the other topic in this trimester program. So there is some advantage for proving bounds in this generality. You potentially, you have applications in a wide variety of situations. So now, let me now turn to the first theorem, our first bound. Okay, this is a general bound, and the bound is going to be expressed in a very simple way. It's just going to be expressed in terms of the size of the derivatives of my polynomial phase. Oops, let me see if I can you see that? Okay. So I take a polynomial of n variables, let me call it f, and I compute its partial derivatives, and I compute their size. I take the absolute value to a certain power. The power is just 1 over the order of differentiation. And I take the maximum of all derivatives of order 1 and larger. That's a finite number, only depending on the degree and the number of variables. And then I minimize. I minimize over all points in the support of my oscillatory integral, in the support of my cutoff function psi. And so I arrive at what's called the h functional of my phase function. This is a nonlinear functional on polynomials. It also depends on this cutoff function psi, but here I want to stress the dependence. It also depends on the absolute value, how I choose to measure the size of my field elements. As we'll see in a moment, that all of these fields will in fact carry an absolute value which will be compatible with the topology, and therefore it will be a non-trivial absolute value because of my assumption that the topology is non-trivial. But not only is there one absolute value on these fields, there are many, many absolute values to choose from. In fact, there's a whole continuum of absolute values. And so we're making a choice here. We're actually choosing a certain normalization of the absolute value in order to express my bound, which will be valid over any locally compact topological field. So I'll come back to that in just a moment. I'll tell you exactly which normalization of the absolute value that I'm choosing here to express this bound in the theorem. But the theorem itself is very simple. It just says that these oscillatory integrals are bounded by a constant times the reciprocal of this h functional. And of course, it's all about this constant. What is this constant? And the most important thing here is that you can choose this constant to be uniform over all polynomials of some fixed degree d. So the constant will depend on the degree. It will depend on the number of variables, otherwise it will be independent of the coefficients. It will also depend on this cutoff function psi, and in certain applications that's important to keep track of. And finally, it will depend on the field K itself. So what do I mean by that? Okay, so for these Euclidean fields, the real and complex fields, what we call the Archimedean fields, there is no further dependence. You just get a uniform constant only depending on the degree, number of variables, and the cutoff function psi. That's it. But for all other fields, all non-Archimedean fields, there is a special finite field associated to them. In fact, all of these fields that we're talking about are hugely infinite, but in the case of non-Archimedean fields, there is an auxiliary field, what's called the residue field, which is finite by our local compactness assumption. And this constant will depend on the number of variables in the residue field. Now, it would be super duper if we could actually show that we can take this constant to be uniform, to be independent of the number of elements in the residue field, but that turns out to be impossible. By example, examples show that this constant has to be at least the square root of Q, where Q is the number of elements in the residue field. And so it becomes an important matter to sort out the precise dependence on this constant in terms of the number of elements in the residue field. All right, so let me now, I want to compare this theorem that I've just written down to a couple of well-known theorems in the literature. These happen to be two of my favorite bounds for oscillatory integrals. They're both in the one-dimensional setting, so with respect to polynomials of one variable, but they're in two different field settings. So in the setting of the real field, there's a very nice bound due to Fong and Stein from the early 1990s. And so they get a bound of these real oscillatory integrals defined with respect to a general real polynomial. And they express their bounds in terms of the critical points of the phase. That's natural. This is the roots of the derivative of my polynomial f. And their bounds express how these critical points cluster. And in fact, they measure that in a variety of ways. One thing that comes into play is the diameter of the critical points. Hello? Okay. Another quantity that comes into play is a bivariant version of the diameter. That is, you take products of pairwise distances between the critical points. And in fact, at every level of multilinearity, there is a notion of the diameter which comes into play. You get an estimate, Fong and Stein get an estimate in terms of all of these quantities, and then they minimize, and they get a super sharp estimate, which in fact is also stable. You perturb the polynomial ever so slightly, your bounds don't change very much. They don't blow up. And that's important in applications. Okay, so Fong and Stein used their bounds for these oscillatory integrals in their study of non-degenerate Fourier integral operators. Right, okay, so let me turn to another estimate that I like very much. This is an estimate due to Loxton and Vaughan. It's even earlier, from the mid-1980s, and the setting here now is the p-adic field. So we're talking about exponential sums. Loxton and Vaughan give a general bound for general complete exponential sums with respect to a general polynomial with integer coefficients. And like Fong and Stein, Loxton and Vaughan express their bounds in terms of the critical points of the phase. Again, the roots of the derivative of my polynomial f, but now they're expressing how they're separated in a p-adic way. And one nice way to do that is via a certain ideal, what's called the different, that is generated by my polynomial, by the derivative of my polynomial. And their bounds are in terms of the size of this ideal, the size of the different, and they measure that with respect to the p-adic valuation. And so, again, it's a very nice sharp result, and the relationship between these two results is the theorem implies both. Okay, you apply the theorem in the case of the real field, you recover the Fong-Stein bound. So the H functional controls the Fong-Stein bound. But if you apply the theorem in the case of the p-adic field, you recover the Loxton-Vaughan bound. Now, I'm not saying it is completely straightforward to see these implications. There is an argument. It's not a difficult argument. It's some sort of combinatorial argument you have to give. But let me stress, though, with respect to the Loxton-Vaughan bound, that implication, it is important, it's imperative that you get the right dependence on your constant in terms of the number of elements in the residue field. You have to prove that you can take that constant to be bounded above by the square root of Q, where Q is the number of elements in the residue field. All righty, so let me now switch gears and let me come back and talk about what absolute value we're using. What is the normalization of the absolute value we're using to express our bounds? And as I said, all these fields carry some absolute value. One absolute value you get is from the modulus of Haar measure. You just fix an element in your field, and that gives rise to a translation invariant measure by just taking a measurable set E and translating it, not additively, but multiplicatively by y, and taking the Haar measure of that. That's a translation invariant measure. And by the uniqueness of Haar measure, that translation invariant measure that depends on y has to be a positive multiple of Haar measure. And so this positive multiple gives me an absolute value which is compatible with the topology. In fact, it is the absolute value we are using in the theorem. It's already normalized the way we want it to be normalized. Geometrically, how you think of this absolute value is that if you look at the balls defined by this absolute value, it interacts with Haar measure in a one-dimensional way. The Haar measure of a ball of radius r is about r. Okay. Now, once we have this one absolute value, you get many absolute values by taking any positive power of it. You can square the absolute value. You can take the square root of the absolute values. These are all absolute values. All of these absolute values will be compatible with the topology. And in fact, you can show you get all equivalent absolute values in this way. You take any absolute value which is compatible with the topology, it necessarily has to be a positive power of the absolute value you started with. And so, and this is convenient because now it doesn't really matter which absolute value we use to compute our H functional with respect to, because if I take two equivalent absolute values, they differ. One is the positive power of the other, and the H functional, this is just by the definition of the H functional, scales accordingly. They differ by the same positive power. So I put this in, I'm slightly colorblind, so I think that's some sort of greenish yellow box. It's a trivial remark, but it will be important. So for instance, if you look at the example of the real field, this absolute value you get by the modulus of Haar measure being one-dimensional Lebesgue measure is just the usual absolute value. But in the complex field, because now Haar measure is two-dimensional Lebesgue measure, the absolute value you get in this way is not the usual absolute value, but it's the square of the usual absolute value. But it doesn't matter because I can relate. If I want to compute, if I have to compute the H functional with respect to this slightly non-canonical absolute value, which is what is how I'm expressing my theorem, I can relate it to the H functional with the usual one, and that'll be important. All right, now what I'd like to do is go back and give a more robust discussion about the sharpness of this theorem. We've already have some indication of the sharpness in one variable, but our theorem is valid in any dimension, any number of variables, any dimension. Let me say, though, that the theorem, first of all, it is not new in the case of the real field. In the real case for real oscillatory integrals, this is actually a theorem due to Arkhipov, Chuburikov, and Karatsuba that goes back to the late 1970s, early 1980s. So they prove exactly the same bound for real oscillatory integrals, but they also make an interesting observation. They illustrate the sharpness of their bound in one dimension in the following way. They show that you take any real polynomial on the real line, you can always find a truncation. Let's assume for simplicity that these oscillatory integrals in this setting is defined over the unit interval. So they show there exists a truncation of the unit interval so that these oscillatory integrals restricted to the truncated integrals have bounds above and below by the reciprocal of this H functional with constants that only depend on the degree. So I find this rather interesting. They prove a general lower bound. Typically, when you want to prove the sharpness of a bound, you exhibit examples to show the sharpness. Here, they show this generally. You get a general lower bound for any real polynomial phase in terms of the reciprocal of this H function. Now, let's be careful. Remember, this is all modulo a truncation of the oscillatory integral, and that truncation depends on the polynomial. But nevertheless, I'm kind of interested in these general lower bounds myself, and I'd like to explore this, but I have a hard time thinking about how to formulate this observation in not only in higher dimensions, but in any setting outside the real field, because their argument heavily depends on the ordered structure of the real field. So I'm going to change the perspective here, not slightly, but maybe I'm just going to change the perspective. Instead of thinking about truncations of oscillatory integrals, I'm going to think about sublevel sets. Okay, we've already seen the importance of sublevel sets in the theory of oscillatory integrals. Just think about Mike Christ's talk or Rui Zhang's talk earlier in the seminar series. But you can also use sublevel sets to get bounds from below of oscillatory integrals. So the sublevel set I'm going to consider is the following. It's going to be defined in the generality that we've been talking about. I'm going to take a general polynomial of n variables with coefficients in this general field K. And now allow me to change the constant term. So up to a constant term, I'm going to measure, I'm going to look at the points in the unit ball, and I'm going to look at this polynomial at unit scale. And then I take the Haar measure of that, and I take the supremum over all the constant terms. And it's well known that this quantity, this sublevel set, is bounded above by an average of oscillatory integrals defined by my polynomial phase f. This relationship, I guess, was first observed in the number theoretic setting, because if you look in the p-adic field, if you unpack the left-hand side, all that's giving you is a count of the number of solutions to some polynomial congruence. In fact, it's a uniform count of a system of solutions to a system of polynomial congruences, and the right-hand side here is just an average of exponential sums. I mean, exponential sums were invented in the first place to count things, to count the number of solutions to an equation or to a system of equations. So in the number theoretic setting, this relationship has been known, I guess, since the beginning of time, but it's also well known in all these other settings. It's just a simple application of the Fourier inversion formula to see that. So we see that oscillatory integral bounds, of course, imply sublevel set bounds, but we can use now bounds from below sublevel sets to get bounds from below of our oscillatory integrals. Now, let me make a remark at this point. So I gave a talk a few months, about, what is it now, 7-8 months ago in a different harmonic analysis seminar series, which happened to also be organized by Marina, among others. So I introduced this sublevel set there, but in the Euclidean setting. But what I had failed to observe at that time is that this sublevel set, so let me give this a name, S sub f. So what I failed to observe that in the setting of the real field, this sublevel set, S sub f, is precisely the sublevel set that Zhang introduced in his talk earlier in this seminar series. He called it, what did he call it? He called it the set of stationary points.
Stationary set. That was, yeah.
Yes, the set of stationary points. And he proved it very interesting about it. He showed that, in fact, you take the oscillatory integral defined by this general polynomial, real polynomial, and you get a bound from above. You bound this from above by this set of stationary points. And he had some interesting applications. So we see from Zhang, well, Zhang and his collaborators, sorry, I know that Xiaoming and Pavel and the others are involved. We see that in the setting of the real field, that there is this tight relationship between the set of stationary points and real oscillatory integrals. We have bounds from below and above. Now, what I want to do here is to explore the relationship between this set of stationary points. I'll continue with their terminology. I want to explore the relationship with this and this H functional. And here's the basic observation. It's very, very simple. We have a general bound from above and we have a general bound from below. This is true for any polynomial of n variables. Now, of course, now this is in the generality of these general fields as well. So this relationship holds. We have a bound from above by a uniform constant times the reciprocal of this H functional. That's a simplified version of the theorem I just wrote down. So that is an even easier, much more trivial observations. You have this general lower bound by the nth power of 1 over the H functional. That just comes from the definition of the H functional. You see that the set of, what was it called, stationary points actually contains a whole ball of radius 1 over the H functional. I've just worked that out in this parenthetical blue remark here. And so we have this general lower bound, and this lower bound matches the upper bound in the one-dimensional case when n is 1. So yet again, when we're in one dimensions, we see how everything is very, very sharp. But in higher dimensions, of course, they don't agree, but you cannot possibly improve any of these two inequalities. And that's because we're proving these estimates. These estimates hold for all polynomials of n variables. And in particular, that includes polynomials of one variable. After all, the polynomial that you happen to choose of n variables could only depend on one of the variables, say the first variable. And so in this case, when you're looking at a polynomial that only depends on one variable, all of these quantities we're looking at, I'm talking about the oscillatory integral, I'm talking about the set of stationary points, and I'm talking about the h functional. All three quantities collapse to their one-dimensional analog, and we've already seen that everything is completely sharp in that setting. So we cannot possibly improve the upper bound. And also you can see that the lower bound cannot be improved by simple examples. Of course, you have to take the examples to necessarily depend on all of the variables. But the remark I want to make here is not only are there examples that illustrate the sharpness of this lower bound, there is an entire family, a rich family of polynomials of n variables with coefficients in my field K, that this lower bound is also an upper bound. And furthermore, you get an improvement on the oscillatory integral bound from 1 over the h functional, that's the statement of our theorem, to the nth power of 1 over this h functional. Of course, that is completely sharp because we have general lower bounds in terms of that quantity. So this is part and parcel of this self-improving aspect, this self-improving mechanism that I alluded to before. And I want to give some details of how this works, because the self-improving bound comes from the theorem itself. Okay, that's why it's self-improving. So let me try to give you the details of how this works in a very simple situation. I'm going to try to explain everything where all the computations are explicit in terms of the setting of complex oscillatory integrals. Because already we've seen there, for complex oscillatory integrals, we've already seen how they can be realized as real oscillatory integrals. So let me in fact make that even more explicit. So I'm going to take a particularly convenient choice, normalization, for my additive character on the complex field. I'm going to take the character that takes a complex number and maps it to the e to the 2 pi I of the real part of that complex number. That's a perfectly nice non-principal additive character. And let me take a general complex polynomial, write it in terms of its real and imaginary parts, p plus iq. Of course, p and q determine each other up to a constant. And now we see that this complex oscillatory integral, this integral over the complex field with respect to this general complex polynomial, is equal to this real oscillatory integral. I'm integrating over the real plane. I'm integrating e to the 2 pi I of this real polynomial of two real variables. And they're the same. But our theorems give bounds for each one separately. Two bounds. When I view it as an oscillatory integral over the complex field, I get this bound of 1 over the h functional of my complex polynomial f. Remember what that involves. You have to compute the complex derivatives of f and measure the size. Now the size is in this theorem that we've taken, we're using a slightly strange absolute value, which is the square of the usual absolute value, but it's related to the usual absolute value by a square here. On the other hand, the same object, I have a bound for this real oscillatory integral in terms of, again, the uniform constant 1 over the h functional now of my polynomial p. And what's involved here, I have to take partial derivatives of this real polynomial and compute the size with respect to the usual absolute value on the real line. Now, as long as I use this, now it's very important here that I am using two absolute values that are related, that are compatible, in order to make the comparison between these two bounds. So it's important to use the usual absolute value on the complex field, because that absolute value is the unique extension of the absolute value of the usual absolute value on the real subfield. okay? And of course, if you take partial derivatives of the real part of a polynomial, that's related to the complex derivatives of the polynomial by the Cauchy-Riemann equations. And so we see that these H functionals, as long as we're using the compatible absolute values, are the same in these two cases. It's a very, and we arrive at this self-improving fact for real harmonic polynomials. So for polynomials, real harmonic polynomials of two real variables, we get a self-improvement of our estimate from 1 over the H functional to the square of 1 over the H functional. Okay, so this self-improvement, we're just applying the theorem. Again, it's by the theorem itself. Now, we can go further. This is not only true for harmonic polynomials. Now, let's just think for a second. How did we arrive at the class of real harmonic polynomials? This was by a choice of coordinates. We chose, I want to think about my complex polynomial as a polynomial of two real variables. And so there is a choice of coordinates that I'm making here. I am choosing a way to represent my complex variable as a pair of real numbers, x plus iy. That's a choice of coordinates. If you like, you can think of it algebraically. The complex field is a real vector space of dimension 2. And I'm making a choice of basis here. I'm choosing the bases 1 and I to represent my complex numbers as a pair of real numbers. That's the canonical basis. But of course, I could have chosen a different basis. I could have chosen 1 and 1 plus I to represent my complex numbers. When I do that, I get a different class of real polynomials of two real variables. They're no longer harmonic. They don't satisfy Laplace's equations, but they will satisfy some other second order elliptic differential equation. And in fact, you can see that there is a one-to-one correspondence between a choice of basis and solutions to a second order elliptic equation. And so we arrive at this family. We take polynomials that are solutions to some second order elliptic equation. And for this family, we have this improvement of the oscillatory integral bound to from 1 over the H functional to the square of 1 over the H functional. Now, of course, you have to check. It's very important. We've checked this for harmonic polynomials, but you need to check this for all these elliptic polynomials, that there is a generalized Cauchy-Riemann equation that allows you to compare the two H functions, allows you to compare the two bounds. And there is. You just take this real second order equation, factor it over the complex plane, you get a first order equation. That's your general Cauchy-Riemann operator for these guys. Right. This is nice. This is how it works out in a simple setting, but this plays out in a rather limited way, as I said before, because the real field does not have too many finite field extensions. It plays out in a much richer way for non-Archimedean fields, because in that case, yes.
We've got a question in the chat about choosing a different basis. Does it give you the same bound for the constant?
You mean when you compare the two H functionals? I guess.
Oh, sorry, Rob. Do you want to ask? Yeah.
No, I would say no. It depends on the constants in your differential operator.
Okay.
Yeah. Sorry, I wanted to ask something different from that.
Okay.
So you said that you could choose a different basis for the complex numbers.
Yeah.
And that gives you a different bound. You look at something other than harmonic polynomials.
That's right.
But I was wondering if that's the same thing, like if you get the same thing if instead of changing the basis, you just change which complex character you use. So you were using the character where you took the real part.
I'm not sure. No, I'm not sure.
Okay.
I'm not exactly sure what you're asking, but maybe we discuss that later, huh?
Yeah, we could talk about it after.
Okay. In the case of non-Archimedean fields, you have this nice feature that they have finite field extensions of any degree n, and there are many of them. So you just fix a pair. If you fix a pair, you fix an extension of degree n, and you fix a basis when you view that extension as a vector space over K. And that generates a subspace of polynomials of n variables with coefficients in the field K. And then you change the basis, you get a different collection, a different subspace. And then you get a whole continuum of subspaces this way. You exhaust it for one field extension, and then of course you could move to a different field extension, and you collect all of these and you get some big rich class of polynomials of n variables. And one can show that in fact you get the self-improvement estimate for all these polynomials. You get an improvement on the oscillatory integral bound from 1 over the h functional to the nth power of 1 over the h functional. Now, of course, again, you have to check for all elements in this family that you generate that you can compare the two bounds, that you can compare the two h functionals. So you can proceed in two ways. You can either work with a generalized Cauchy-Riemann equations in this setting. There are. It becomes rather complicated to try to characterize these polynomials as solutions to second order equations. In fact, when you go beyond quadratic extensions, cubic extensions and beyond, it's no longer, you cannot characterize them by one second order differential equations. Now you have to work with systems. But there's an alternative. There is an abstract approach to this comparison. So in this abstract approach, we identify a key feature to these polynomials that we're looking at. They have to be in some sense depend on all of the variables. And this key property is some sort of open mapping property that they have. And that's what one proves in a more abstract way. And that allows us to make this comparison more directly without going through differential equations. Right. All right. Now let me just, I think I am running out of time here. So, oops, yeah, okay, so let me stop. We can continue playing games. In fact, you can now formulate higher dimensional versions of the Fong-Stein bound. You can formulate versions of the Loxton-Vaughan estimate for multiple exponential sums. But let me forego all of that because I do want to say something about this very simple elementary argument that we have in order to treat oscillatory integrals in this generality. And actually everything, so let me skip to the end here. Here we go. Everything boils down to one simple lemma. This is what we call the key lemma. It's just a lemma about polynomials in one variable. You fix, in fact, this is such a useful lemma. This lemma, actually, you can use it to prove this open mapping property for these family of polynomials that have the self-improvement feature. It's extremely simple. You just take any point in your field, you look at your polynomial at x, at this point x, you look at the derivative at x, and you let r be a positive parameter that controls the ratio of the sizes of these two quantities. And what you can conclude is that there is a nearby zero of some derivative of your polynomial, which is close to x, whose distance to x is at most a constant, a uniform constant times r. And this uniform constant you can take to be 1 in the Archimedean setting, and you can take it to be a to the d, where d is the degree in the Archimedean setting. Now, let me make a trivial remark. This inequality is scale invariant. I scale my polynomial any way I like, nothing changes. That's a trivial remark, but an important one. If there are any number theorists that are listening, they might see this lemma. It looks like a kind of Hensel, formulation of Hensel's lemma from elementary number theory. And in fact, that is exactly the right point of view. This lemma, you should think of it as a scale invariant formulation of Hensel's lemma. Hensel's lemma itself is very, very non-scale invariant. And that is because Hensel's lemma imposes an additional non-degeneracy condition on the derivative of my polynomial at x, and it also imposes conditions on the coefficients. They have to be bounded. They have to lie in some ring of integers. Here we get rid of all of those conditions. We drop them. of course, we pay the price. We pay a price. The price we pay is that we no longer find a zero of the polynomial itself. That's what you get from Hensel's lemma. But you find a zero of some derivative of the polynomial close by. But for us, that doesn't really matter. It's just the total number of nearby zeros that matter. And whether I'm looking at the zeros of my polynomial or throw in all the zeros of the derivatives of my polynomial, still the total number is controlled by a constant only depending on the degree. And that's what's important. Now, for those that, now we can use the power of scale invariance. And of course, I know that those people that work with oscillatory integrals in the Euclidean setting know the power of working in a scale invariant way. One thing that often happens is once you have a scale invariant inequality involving the first derivative, that by itself, scale invariance by itself, will imply the exact same inequality, scale invariant inequality for higher order derivatives. And that is what happens here as well. So we get as a consequence the same result, but now instead of the first derivative, we have now the kth derivative that we're relating. And now, of course, these are pointwise estimates. If we had a measure, and we do, we have Haar measure, we can translate these pointwise estimates into a bound for a sublevel set, a local sublevel set, which is a more robust object. I don't need to assume that the kth derivative of my function is globally bounded below. I'm only going to look at points where my kth derivative is large, at points where my function is small. And by taking this local perspective, this is a more powerful, this is a perspective. One nice thing is once you prove a bound for functions for a local object of one variable, you automatically get it for functions of many variables. So we get as a consequence, and this is the key consequence here, we get a scale invariant bound for local sublevel sets for polynomials of many variables. I take a polynomial of n variables, coefficients in this general field K. I look at points in the unit ball where my polynomial is less than epsilon by some other derivative. Kth order derivative is bigger than mu. And the Haar measure of that is bounded by a uniform constant times epsilon over mu to the 1 over K. And now the proof is immediately, because everything is local. This does not work if you're not working with a local sublevel set. I have this set inclusion. It's a pointwise. I take a point where my polynomial is less than epsilon, but where some partial derivative is bigger than mu. And of course, I can write that partial derivative as a linear combination of pure kth order derivatives in a given set of directions. The total number of directions is only controlled by the degree and the number of variables. And so by taking the measure to both sides, I'm reducing to looking at a sublevel set of a local sublevel set, but now my differential operator is a kth order derivative in a direction u. I take my polynomial of n variables, I restrict it to lines in the direction of u. That's a polynomial of one variable. I invoke my scale invariant observations for polynomials in one variable, and I integrate out in the other variables by Fubini. That's it. And we get this scale invariant bound. Now, let me remark, this scale invariant bound is false if you move from polynomials to analytic functions. There are simple examples of analytic functions in one variable where there is no scale invariant bounds for local sublevel sets. It's of course true for the traditional sublevel sets where you suppose some global bound on your derivative from below. All right, now let me, and I think I've now completely run out of time here, but I've just got one. And now I just want to convince you how simple now, how you use the scale invariant inequality for local sublevel sets to treat oscillatory integrals. In fact, you can even do better. You can treat local versions of this oscillatory interval. Okay, but let me now, okay, I'm running out of time. Let me just stick to traditional oscillatory interval. And the idea is you want to analyze this at the scale given by some functional, depending, which is not of my polynomial phase. It's not the H functional, but it's a cousin, what I call the J functional. It's defined in exactly the same way, except it only involves derivatives of order 2 and larger, no first order derivatives. And a nice feature about that this, just from its definition, it's locally constant at the scale of 1 over the J functional. And so I can use this to organize my oscillatory integral in a very precise quantitative way. I can split the integral into two parts where the phases become stationary, and that's precisely the place where the gradient is controlled by this J functional, and where the gradient is large compared to the J functional, I have a lot of oscillation. So everything is quantified now. And for the place where the phases become stationary, I don't do anything. I just put in absolute values and I have this sublevel set. It's a local sublevel set. It's where the gradient is less than the J functional. I just apply my scale invariant inequality and I get the bound I'm after. Now, in the case of where you have oscillation, what happens is that you can control that also by a sublevel set. Now, the sublevel set here is where the gradient is larger than the J function. That's huge. That's almost the whole integral. But it's a weighted, you can control it by a weighted local sublevel set estimate. Now, I've written it out. Now, how it manifests itself is slightly different depending on whether you're in the Archimedean case or in the non-Archimedean case. I've written it out here in the Archimedean case. It's easy to see this weight. And in order to prove it in the Archimedean case, all you have to do is integrate by parts. We're perfectly in the situation where we can integrate by parts as many times as we like. That's because we have a bound from below of our gradient and bounds above on all the other derivatives. And that's exactly what you need in order to integrate by parts as many times as you like. And if you do that, you just get this weight, and this weight is manifestly small on this large set. And so all we have to do now is split this weight up to where it's roughly of a certain size, pull it out of the integral, and I just apply my scale invariant bound for my local sublevel sets, add things up, and you get the bound. Okay, it's that simple. Now, in the non-Archimedean case, it's a slightly different. This weight is more discrete. It's either 0 or 1. Okay, so when the gradient, how you can't in the discrete case. One slight difference here is that you cannot integrate by parts effectively. But when you see a lot of oscillation, that indicates in the non-Archimedean world that there should be perfect cancellation. You should see 0. And that's true when the gradient is much larger than the J functional. This weight is small. Then you actually get 0 by seeing that part of it as a sum over all characters of some quotient group. You see, you just use the basic property of characters, the orthogonality property of characters. But there's a problem when the gradient is about the J functional. There you don't get perfect cancellation, but then there's not too many pieces left over. You can either do two things. You can do nothing, which is what I like to do, and you see that you still get a bound in terms of 1 over the H functional, but your constant depends badly on the number of elements in the residue field. You get it worse. This argument always gives you a linear dependence, Q. But if you want to do better, which you have to do if you want to recover, say, the Lux and Von estimate, what you can do is organize the remaining bits into an exponential sum over a finite field. And an exponential sum over a finite field, one way to view that is a weighted count of the number of points on some curve or surface. And since finite fields have no scales, that is just a weighted local sublevel set bound, for instance, and you can get the extra square root cancellation. Anyway, all right, I've gone over. I apologize, so I will stop there. Thank you for listening.